Hello, this video lecture corresponds to Chapter 6, Second Law of Thermodynamics. I'm recording this for the session that I'm not available to teach the class in person. Um, so we're going to continue the discussion and we will do some examples when I'm back from the conference. Okay, so in continuation of our discussion, we're going to introduce a new concept which is reversible versus irreversible processes. If you remember when we were talking about the efficiency of heat engines in the class, I told you that no heat engine can have efficiency of 100%, and this is not because we have a lot of friction in the system. It's because there is a theoretical cap on the amount of efficiency imposed by second law of thermodynamics. So this motivates us to define a perfect situation in which no friction exists and no imperfections appear in our system. That situation happens when we have a reversible process. A reversible process is a process that can be reversed without leaving any trace on the surrounding. On the other hand, irreversible processes are processes that are not reversible. For example, if you think about this frictionless pendulum as it moves to left and right, if there is no friction, this process is very reversible because when it goes all the way to the right, it can then comes back all the way to the left and can continue this forever. This is an example of a reversible process. But if there is a friction between air and this pendulum, what happens is at the very end, you will have a stationary pendulum. So that will be a irreversible process. Another example is quasi-equilibrium expansion and compression of a gas. So if I have a gas trapped in this piston and I move this in this cylinder and I move this piston to the left, and I do that in a very slow manner, the process will be quasi-equilibrium, which means then I can return the piston to the right um, in a quasi-equilibrium process and be back on the place that I started. So these processes are totally reversible. Reversible processes are ideal situations that we got rid of all the imperfections, all the causes of irreversibility, for example, friction. Now, in this slide, we're going to look more into what a reversible process means. So all the processes occurring in the nature are irreversible. There is no way we can eliminate all the frictions, all the imperfections, all these type of problems in our system. So uh, a reversible process is a process that we engineers imagine in our brains so that we can simplify our lives and do our analysis. So why are we interested in a reversible process? First of all, they're easier to analyze. If I don't have to deal with friction, my life is going to be much easier. And they serve as an idealized model to find the theoretical limits to which actual processes can be compared to. When I told you in class that there is always a cap of efficiency, I didn't tell you what that cap is, but I just told you that it exists. In order for us to find that cap of efficiency, we have to we have to work with an idealized model. And the idealized model that we are going to imagine is based on reversible processes. Turns out some processes can be more irreversible than the others, in the same way that some bearings are worse than other bearings. They waste more mechanical energy. So here's an example. We try to approximate reversible processes. Why do we care? Why do we want to approximate reversible processes? Because these processes serve as the ideal model for us. We can now understand what is the maximum efficiency that I can get, how good my system can get to from theoretical perspective. Now, work producing devices such as car engines and gas or steam turbines, they deliver the most work if the processes are reversible. On the other hand, work consuming devices such as compressors, fans, and pumps, which consume the least work, they consume the least work if when reversible processes are used instead of irreversible processes. Bottom line, if you get rid of all the imperfections, if you work with the totally reversible processes, devices like engines and turbines, they deliver the most work. Devices that consume work like compressor and fan, they consume least amount of work. Now, if you look at on the figure here, uh, this is another example of a reversible versus an irreversible process. So if I have this situation, water behind this barrier, of course there will be some pressure formed. I can move this to the right and expand the system, or I can move it to the left and compress the water, but and this will change of course the pressure distribution. If I do this slowly, I can clearly predict the pressure distribution and there will be very reversible. I can again go back to where I was, the pressure distribution will go back to what it was. Now, think about a fast expansion or fast compression. In this case, you will generate some wave behavior, and this will cause irreversibility in the system. Okay, now what are the irreversibilities? Let's understand what can cause irreversibility. Excuse me. The factors that can cause a process to be irreversible are called irreversibilities. They can be many things. The most intuitive cause of irreversibility is friction. If you have friction in your system, that's a cause of irreversibility. But there are other examples, other causes of irreversibility. For example, if I have unrestrained expansion, if I have uh, a system that expands unrestrained, I let the piston just expand in a very unrestrained way, or let the gas expand very fast. These two, all of these three basically, fast compression, fast expansion, or unrestrained expansion, they are causes of irreversibility because we cannot go back and be at the same place. If we have a mixing of two fluids, it's not really possible to separate them again in a reversible way. A very common form of irreversibility is heat transfer across a finite temperature difference. So if I have a soda can here, uh, which is at 50 degrees C, I'm sorry, it has a 5 degrees C, and we leave it in a room which is at 20 degrees C, of course the heat will be transferred to the soda can, and there is a finite temperature difference between 20 degrees C and 5 degrees C. Therefore, the soda will get warm and eventually will be at 20 degrees C. This process is also irreversible. I cannot remove the heat back uh, and bring the temperature back to 5 degrees C. This doesn't really happen in nature. Okay. Also, there are less common forms of irreversibility. In elastic deformation of solids, there are permanent changes, they're irreversible, and chemical reactions are also considered irreversibilities in the system. So if you have any of these in a system, within the boundaries of the system or in the surrounding, then this process is called irreversible process. We categorize reversible processes in two um, main category and one summation basically. So internally reversible processes are situations that you have no irreversibility occurring within the boundaries of the system during the process. If within the boundaries of the system here inside the system I don't have any friction, any heat exchange in or any chemical reaction, this process is internally reversible. So if no irreversibilities occur outside the system in the surrounding, we call this system to be externally reversible. A totally reversible process involves no irreversibility within the system or its surrounding. So this is an example of a totally reversible process. No irreversibilities outside, no irreversibilities inside the system. We're going to refer back to these definitions in the class uh, when we talk about second law of thermodynamics again. A totally reversible process involves no heat transfer through a finite temperature difference, no non-quasi equilibrium changes, and no friction or other dissipative effects. If your heat transfer from the surrounding to the system happens through a very small amount of temperature difference, then this process can be assumed to be reversible. So note that if this heat transfer happens from a surrounding which is at almost 20 degrees C, just above 20 degrees C, to a system which is at 20 degrees C, this heat transfer is reversible. But if a heat transfer is happening from a 30 degrees C environment to a 20 degrees C system, this is a cause of um, this is a cause of external irreversibility. Although the system may be internally reversible, the presence of this heat transfer makes it uh, externally irreversible. Therefore, the system is not totally reversible. Note that for heat transfer to exist, you always need that temperature difference. But the more the temperature difference, the more the system will be irreversible. Ideally, for a reversible process, you want the heat transfer to happen between a very small amount of temperature difference. Okay, we're going to use this concept to develop a reversible cycle. So a reversible cycle, which is called the Carnot cycle, is the most efficient power generating cycle. You can think about it as a piston cylinder device as before, which goes through four different processes to generate power. First, in the first process from point 1 to 2, we have um, a gas inside the piston cylinder at a constant temperature and a heat transfer happening at that constant temperature. You may say, okay, these are two at same temperature. How can this happen? But the answer is the temperature of the source is just above the temperature of the gas. So the heat transfer exists just because of that tiny little temperature difference. So this heat transfer happens in a reversible way because it is not happening in a finite temperature difference. So as a result of this heat transfer, you will have an increase in the volume, and the process is of course isothermal. Now that the piston is here at point 2, we're going to remove this energy source and insulate the top of the piston, and we'll continue the expansion. But this time, this expansion is not happening in an isothermal way because there is no heat transfer happening to make it isothermal. It is actually happening in an adiabatic process because we have isolated the piston. So further expansion in an adiabatic process when we land on point 3. Now we are at the bottom of this cylinder. We are in the bottom dead center technically. So now we go from point 3 to point 4. We have a compression, but this compression happens at again a constant temperature of TL. In order for this to happen, We remove the insulation, we replace it with an energy sink, which is just below the temperature of the gas TL. So we will have a heat transfer QL due to a tiny little temperature difference between the energy sink and the system. So we can safely assume the temperature remains constant from point 3 to point 4. So therefore, the process is isothermal. At point 4, again, we remove the heatsink and we add the insulation and we continue the expansion. We continue the compression from point 4 to where we started, meaning point 1, in an adiabatic process. Since no heat can be rejected, as we continue the compression, the temperature will go from TL all the way to ATH. So we had four processes. Process 1 to 2, temperature is constant, isothermal expansion. Process 2 to 3, adiabatic expansion, temperature drops from TH to TL. Process 3 to 4, which was a constant temperature isothermal compression process, and from 4 back to state 1, temperature rises from TL to TH through an adiabatic compression. So it was a cycle that the gas went through, and as a result, this piston went to the from the top dead center to the bottom dead center, and again came back to the top dead center. Therefore, it generated mechanical work. And turns out, if we could have such a system in reality, this system is going to generate the most amount of work, because all the processes that we describe here are reversible processes. This is a reversible cycle. A guy named Carnot came up with this idea, therefore we call this a Carnot cycle. Now let's plot what we just described on a PV diagram. Again, from 1 to 2, happening at constant temperature. Now, this is a constant temperature line. Constant temperature lines appear like this on a PV diagram, as we know, and it's a gas. Therefore, we don't have any dome here. Dome is way to the left. We don't even see it. So from 1 to 2, we have heat addition on a constant temperature line. From 2 to 3, we further expand the system. From 2 to 3, volume is increasing, but this is happening in an adiabatic process. So from 2 to 3, this is an adiabatic line. They're similar to constant temperature lines, but their slope is more. From point 3 to 4, this is again a isothermal process, but it's a compression. So this is a compression from point 3 to point 4, and from point 4 to point 1, we have an insulated cylinder, so it's an adiabatic compression from point 4 to point 1, and we are back to the place that we started this cycle. So if you think about it, now we have done a thermodynamic cycle, and this thermodynamic cycle is generating work for us. What is the amount of work that is generated in a thermodynamic cycle? If you remember from previous lectures, if we have a thermodynamic cycle on a PV diagram, the amount of work generated is the area trapped between the processes of the cycle. So the area inside here is the amount of work that is generated. Okay, we could look into the reversed version of the cycle that we just described. This time, the reverse Carnot cycle is simulating a Carnot refrigeration cycle. So the Carnot heat engine cycle is a totally reversible cycle. Therefore, all the processes that compromise it can be reversed, in which case it becomes a Carnot refrigeration cycle. With the same logic, the work needed in this reverse Carnot cycle is the area inside this cycle. So note that it's exactly the same cycle compared to this one, except for the direction of the processes are reversed. So when you have a clockwise cycle, it's always a power generation cycle. If you have a counterclockwise cycle, it is actually consuming some work, and it's most likely a refrigeration cycle. Okay, now let's think about the followings. We should discuss the Carnot principles. Carnot principle has two important messages for us. First, the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one, operating between the same two reservoirs. Well, this is kind of intuitive because, of course, these irreversibilities are going to, make the system to be less efficient, so to speak. Think about it as friction, for example, which is causing the efficiency to be lower than its maximum potential. So this is obvious. Second message of Carnot principle is the efficiencies of all reversible heat engines operating between the same two reservoirs are the same. So if I have two reversible cycles, in this case, operating between a high temperature reservoir TH and a low temperature reservoir TL, these two heat engines are both reversible, therefore they will have the same efficiency. You can't be more perfect than perfect, right? Both of them are perfect, therefore they will have same efficiency. On the other hand, both of these guys will have a higher efficiency when compared to an irreversible heat engine. This is obvious because the irreversible heat engine has irreversibilities inside or outside of it, which is uh, decaying the amount of efficiency that you can gain. Now let's figure out what is this efficiency? What is this maximum efficiency that we talk about? What is the theoretical efficiency that we can achieve in a heat engine regardless of frictions and everything? If we have a totally reversible cycle, what is the maximum efficiency we can gain? In order to understand that, we should first uh, agree on this state in this equation. This equation says, and we can derive this mathematically, but it's beyond the undergraduate course, so we're gonna skip that. But we should agree that the ratio of the heat transfer from the heat source to the ratio to the heat transfer to the low temperature source is going to be equal to the ratio of high temperature of the reservoir over the low temperature of the heat sink. So again, ratio of heat transfers QH over QL for a reversible heat engine, which is a Carnot cycle, operates on a Carnot cycle, is going to be equal to the ratio of the temperature of the heat source and heat sink. And make sure you always use Kelvin scales when we're thinking about this equation. So knowing that, we know for any heat engine the efficiency is 1 minus QL over QH. We derived this in class. This is for any heat engine, no matter if it's reversible or irreversible, you can always write this. But this ratio tells me I can convert 1 minus QL over QH to 1 minus TL over TH for a reversible cycle. So if you're thinking about a Carnot heat engine, then this equation is replaced by this one, in which you only have temperatures, and again we make sure these temperatures are always written in Kelvin scale. Now this value of efficiency can give us very interesting values. So if I know the temperature of the heat source and the temperature of heat sink, I can find the maximum possible efficiency of a heat engine that can operate between these two. So if I use the temperatures here, then I will find a value for efficiency of a reversible cycle which no heat engine in reality can reach to. Therefore, comparing to a real heat engine, If the efficiency of a real heat engine is smaller than the efficiency of the Carnot efficiency, then it's an irreversible heat engine, of course, because it's smaller than that. If it's equal to the maximum possible efficiency of Carnot, then there is no way this can happen except for that cycle is also reversible. And if you're thinking about a situation that the efficiency of cycle is more than the theoretical cap, this is an impossible heat engine to achieve. So if I tell you I have a heat source from like a furnace or a nuclear reactor or a solar field, which is at 1,000 degree Kelvin, and I have a low temperature reservoir, let's say an ocean temperature or a river temperature at 300 degree Kelvin, you can simply plug in these values here and tell me the efficiency of the most efficient heat engine can exist between and operate between these two. Now here's more on that. So consider the efficiency of a reversible cycle and the heat engine that is reversible. If I keep the low temperature reservoir at 303 degree Kelvin and I change the temperature of high temperature reservoir from 350 all the way to 925 degree Kelvins, if I plug in all these values in this equation, the maximum efficiency possible will change from 13.4 all the way to 62.2%. So now here's the question. How do you increase the thermal efficiency of a Carnot heat engine? Of course, you want this ratio to be as small as possible. Therefore, 1 minus this ratio will be the closest to 1. How can you reduce this ratio? How can you make it small? You can either reduce the numerator, basically decrease the temperature of the reservoir, or you can achieve the same objective by increasing the temperature of the hot reservoir. So if you're operating a power plant here in Los Angeles, and you move the same power plant to North Pole, because the temperature of the low temperature reservoir, meaning the environment is going to be smaller in North Pole, the efficiency of the power plant will increase as a result of that. Or if I keep the low temperature reservoir the same and I operate at higher temperature, I have more potentials to achieve. It doesn't mean that I necessarily achieve to that, but the cap is now higher. The theoretical cap on the efficiency will be higher if the temperature of the hot reservoir is higher or the temperature of the cold reservoir is lower. Okay, in the other words, the thermal efficiency of actual heat engines can be maximized by supplying heat to the engine at the highest possible temperature, limited by material strength, and rejecting heat from the engine at the lowest possible temperature, limited by the temperature of the cooling medium such as rivers, lakes, or atmosphere. Bottom line, you want TH to be higher, you want TL to be lower to achieve better efficiencies. This brings up the idea of quality of energy. So if my thermal energy is at a higher temperature, then it has a more quality, because remember that higher temperatures means TH is higher and this ratio is smaller, therefore the maximum possible efficiency of a reversible cycle is closer to 1. So for that reason, the same amount of energy, the same amount of thermal energy at higher temperatures has more potential. Same amount of thermal energy in lower temperatures will have lower quality of energy. Here are two examples. Concentrating solar power plants operate based on concentrating the solar energy into a line, into a pipe. So a fluid is pumped through this line, and these parabolic troughs, they concentrate the solar energy on this line, and they heat up um, a working fluid, let's say an oil or gas or something. This can reach to temperatures as high as 400 degrees C. Therefore, the efficiency of a conventional power plant that uses a parabolic trough solar field as a heat high temperature source is usually in the order of 35% to 40%. On the other hand, you can use the same sun and operate a power cycle, basically a power plant, using a solar pond. Solar ponds are situations like this in which there is an absorber at the bottom, so the solar energy penetrates through the layers of water and is absorbed down here. So the temperature at here will be about 90 degrees C, while the temperature up here, due to losses and everything, is still at 20 to 35 degrees C. There is of course a potential for power generation. I can establish a heat engine between these two temperatures and generate some power, but the efficiency will be dramatically smaller. In fact, it's just about 5%. Okay, now we can think about the refrigeration cycles exactly in the same way that we thought about heat engines. So if we have a cool refrigerated space at a low temperature and a warm environment at a higher temperature, then a reversible cycle will have will have a maximum value, and all the irreversible cycles will have a smaller coefficient of performance compared to the reversible refrigerator. And we cannot achieve a coefficient of performance that is higher than the coefficient of performance of a reversible refrigerator. So this is impossible refrigerator. This is a irreversible refrigerator because its coefficient of performance is smaller than the coefficient of performance of a reversible cycle. So in this, we can find the coefficient of performance of a refrigeration system or a heat pump using these two equations. Again, we derived these two in class. But for a Carnot refrigerator or heat pump, which is totally reversible, we replace the ratio of heat with the ratios of heat temperatures if the temperatures are given in degree Kelvin. As a result, this equation will convert to this one, and this reversible is shown here. So if I tell you what is the maximum coefficient of performance of a refrigeration cycle operating between TH and TL, you can tell me, you can use this equation to find that. And in order to find the coefficient of performance of a heat pump operating between those two temperatures, we use this equation. And both of these are giving the maximum theoretical possible coefficient of performance for a refrigerator or pump. Okay, this summarizes this video lecture, but we will do a review of these concepts in class on the following week, and we will go over some examples, numerical examples in class. Your Learn Mine assignment 6 is still due on 17th. Your homework 6 has now an additional part 2, corresponding to irreversibilities and Carnot cycles. Thank you very much for watching the video.